Okay, guys, today we're looking at hydrolysis of salts. This is sort of the last, I guess, big section within this chapter we're going to look at before our next test. And so hydrolysis of salts is kind of grouping a lot of different things you've learned into one big sort of section here. So we're going to be pulling up on a bunch of different stuff. So you will need your data booklets. I will get started with that. Okay, so let's take a look at something like sodium chloride. And if you put that into water, what would you think happens to that salt? Well, it's going to dissociate, of course, into sodium ions. And it's going to also produce some chloride ions. And that would be aqueous. Now, of course, what we've learned is that if you put certain compounds in water, they can produce hydronium ions, and that would be classified as an acid. And they can also produce hydroxide ions, which would be something we associate with bases. And so what we're curious about is would putting sodium chloride into water affect the pH of the water? Would the pH be affected by this? So would pH change by adding sodium chloride to a glass of water? So you have this glass of water, and you throw some of this chemical in there. Would the pH be 7, or would it go above 7 or below 7? And so we have to know kind of what these ions would do in solution. So our data table really is really important for us to be looking at now to sort of determine whether or not they would have an influence. So let's take a different example, see if we can compare two salts. Sodium chloride is a very common salt, but let's pick one maybe not so common, something like NaF. And I'm choosing the alkali ion sodium here so that there really is similarity between the two compounds, but also the difference here being that of the anion, that is the negative ion that we're looking at. And so let's say you did the same thing. So I'm going to take a glass of water, and I'm going to throw some sodium fluoride into the water. Would that change the pH of the water? Would you get an alteration of the pH? Would it become more acidic, more basic, or does it just stay neutral? So let's take a look at our ions here. Let's take a look at sodium ion. So I'm going to put sodium over here, and I'm just going to do the sodium for both in this little calculation here. And I'm going to say, let's say you put sodium with water. Sodium ions bumping into the water molecules now. So do you think sodium would take an H from water? Like, do you think it would take a hydrogen atom from water? Let's take a look. It would get nah. What do you think? Nah? No, you're right. Nah. Actually, it would be nah. No, that's not going to happen. That would be weird. So it'd be strange for a positive ion to take another positive ion. In fact, that would actually be 2+ if that was true. And so we know sodium does not do that. And can sodium act as an acid? Well, it doesn't have any H's to give, so it can't act as an acid. So if you think adding sodium chloride to water would have no effect on the pH of the water, you would be correct. That would be, it should be a neutral. So we actually refer to sodium chloride as a neutral salt. At least the sodium ion, I should say. Now the chloride, let's take a look at the chloride ion now. So let's take chloride, choose red here maybe. So chloride is a negative charge. Okay. So can chloride ion, can it be an acid? Well, to be an acid, you have to have an H to give, which it does not have, so it cannot be an acid. But could it take an H? I mean, it's got a negative charge. So let's take a look. Let's say you give it an H. You get HCl, and you get hydroxide. So I guess the question is, does chloride ion do that? Like, would it actually act as an acid, or as a base in this case? So let's take a look at our data table. So pull the data table up. And we will notice that, where is it here? So we got to see, is chloride going to act as a base? Well, there it is as a base. So it is on the table, it's a base. But it cannot act as a base. The reaction shows it can only go one way. And that's because we know HCl is a strong acid. It should ionize 100%. So this particular reaction would not occur either. So this is not something we would see happening. So that's not going to occur. So that means that sodium is neutral in water, and chloride is neutral in water. So the salt sodium chloride, this is an example of a neutral salt. It has no effect on the pH of the water. So can the same thing be said true for sodium fluoride? Let's take a look at sodium fluoride. Well, we know sodium fluoride would also dissociate into sodium ions and fluoride ions, and they'd be aqueous states, so they would be bumping around with water. And we know from the previous question that sodium ions are neutral; they can't change the pH. So let's take a look at the fluoride ion. Figured out if something could happen with the fluoride. So I'll use red for the fluoride. And we react it with, actually I'm going to use, let's do a more clever color for this because I sort of know what's going to happen here. So let's take a look at blue. And so we'll say the fluoride ions reacting with water. Would they be able to act as an acid? Well, just like chloride, no, that's not possible. There's no H's to give up. But fluoride does have a negative charge. So is it likely to take H's and produce something like HF? And then the water, being the acid here, would donate a proton, so it becomes hydroxide. So let's take a look at our data table again. So I'll pull the data table up, jumping around here. And fluoride ions, now they're also right here. There we go. And they are the conjugate base of the weak acid HF. And so we notice these equilibrium arrows here. That means the reaction can go in reverse. So this particular reaction, that can occur. So you do get some hydroxides being produced here. So since NaF produces hydroxide when added to water, we say that sodium fluoride is not a neutral salt. It's actually a basic. It's actually a basic salt because it changes the pH of water by making hydroxide, so the pH would go above 7. Okay, so what does this word hydrolysis mean in the first place? Well, generally it's related to the reaction between salts and water, and really the cations and anions of those. So the first reaction, I'm just going to rewrite a different reaction here, and we'll sort of work through it, and let's sort of try to explain hydrolysis as we go through it. Because I kind of gave you examples above of what could be hydrolysis, but let's actually go through the hydrolysis of a different salt that we haven't looked at yet. So let's pick a salt like, let's go to my data table here. Yeah, there we go. Let's take a look at, oh my God, I lost it. Oh yeah, there we go. Potassium oxalate. Okay, so first of all, that is a salt. So we have to remember from the solubility chapter that when you add a salt to water, it's going to undergo not just dissolving, but dissociation. And so the idea that you get ions being produced in solution is sort of a characteristic of the idea of a soluble salt. So the soluble salt should produce 2 potassium ions and 2 oxalate ions. So that's just dissociation, though. So that's not nothing new. That's basically what you knew from grade 11 chemistry and also from we did in grade 12. But the question now becomes, could potassium act as an acid? Is it possible that the potassium ions would react with the water in a way that changes the pH of the water? Well, they can't be an acid because they have no H's to give. And they also cannot act as a base because they can't take hydrogen from water. I've never seen something like KH 2 plus or something like that. It seems strange to me. So this reaction here is no reaction. So we would say that the alkali ions are spectator ions here. Okay, now what about the oxalate ion though? So the oxalate ion is C2O4 2 minus. And if you react that with water, well, once again, it could not be an acid. We've kind of gone through this. And I guess the question is, can oxalate take an H? So once again, go back to your data table. So I'm going to jump back and forth here. And if I just erase the ones I've done already, and I look for oxalate ion, oxalate ion is right there. And we see these equilibrium errors, which means the reaction can go backwards, which means it can take an H, and you get the conjugate base hydrogen oxalate. And let's sort of go back here. So this will, in equilibrium, form some amount of HC2O4 minus. And then what would the other ion be here? Well, that compound is acting as a base, so the water must be acting as an acid. So once it gives its H, its conjugate base would be hydroxides. So once again, this is another example of a basic salt. But we're just trying to talk about the process of hydrolysis. So this first part here, I'm just going to put a sort of highlight in green here. That's your dissociation. That's chemistry 11, and obviously a bit of 12. And it's actually this part now, this part here, that's the hydrolysis part of it. So the salt dissociates, but then the ions of that salt will ionize the water, so it will turn into hydroxide in this case. And we'll go through some examples where you're actually getting an acid being produced here. Okay, so let's take a look at, yeah, it's a good one to choose. Let's just try, just gonna use examples. Let's take a look at ammonia. I'm going to take chloride again because we sort of know what chloride does. But if you put ammonia chloride into water, you're going to get ammonium ions. Ammonium chloride, she said. And you're going to get chloride ions. Now, from the previous example, we saw that chlorides are the conjugates of strong acids, so they don't actually act as bases, but they are technically a base. You could classify them as that, but they don't act as a base. They wouldn't affect the color of litmus paper. They wouldn't taste bitter or anything like that. But the ammonium ion, well, what is that? The ammonium ion is actually, if you look on the data table, I'm going to not skip back and forth with this one, but that's actually a weak acid. And so you wind up getting an equilibrium between itself and its conjugate base, ammonia. But what would the water be ionized into? So once the ammonia comes in contact with, you get this hydrolysis. So what would you get forming here? Well, you're going to get the conjugate acid of water, because the ammonium is acting as the acid, so the water must be acting as the base. And so you get hydronium being produced. And that means the pH would go below 7 now. So we refer to this salt as an acidic salt. Okay. Now, there are definitely some stuff or some examples we're going to come across here, and they are maybe a bit contradictory to what you might think, and maybe some aren't. Maybe they seem pretty reasonable here. So I'm just going to pause the video, and then I'm going to continue after that. So let me just unshare here. Stop sharing. Okay, so here's some examples here. Sodium bicarbonate and ammonium nitrite. And what I did is because we couldn't do a lab, I used this, I like this lab a lot actually, but this is the results I got from students last semester who did this. And when they put sodium bicarbonate into water that had a chemical called universal indicator, it turned sort of a bluey kind of color. And when they put ammonium nitrite into water, it turned kind of yellow. Now, previous to adding the chemical, the water was a green color actually, and it changed color as it was added to the solutions. So I'm going to flip over to maybe a different video here, or a different slide here, and just sort of show you what we're talking about here. Okay, so this is the color range for a chemical called universal indicator. So depending on the pH, you get these various colors that can form. And so you can see the red at one end, that's quite acidic, all the way up to purple at the other end, which is obviously quite basic. So colors like green and blue, they're more on the basic side. And your oranges, your yellows and stuff are in the acid range. And a green kind of color indicates neutral. So that's kind of what we mean by the color charts here. So you can go back on this video and look at this if you want to. Where are we going to slip back to this? There we go. So why would the water turn blue here? Well, if you take sodium bicarbonate, we know that it dissociates into its ions, sodium, and we know it dissociates into bicarbonate. Now, it turned blue, so we can kind of deduce that it's acting as a base. But what part do you think would be acting as the base here? Well, maybe it's the bicarbonate, because we know the sodium is neutral in water. But the thing about bicarbonate is it's actually amphiprotic. It has properties of acids and bases. So it actually would give a proton. It would form carbonate, and that would make hydronium, which would make it acidic, which means it should have been red actually. But then it also has basic properties, which means it can take a base and form H2CO3 and hydronium. Or hydroxide, sorry. So what does it do then? I mean, obviously it turned blue, so it must have made hydroxide, but it actually does do both. And so what we need to look at are K values here. So the Ka for HCO3 minus is equal to, according to the data table, bicarbonate ion, 5.6 times 10 to the minus 11. So it does produce quite a small amount of hydronium. And now its Kb value would be Kw, 1.00 times 10 to the minus 14, divided by the Ka of the conjugate acid, which is carbonic acid. So 4.3 times 10 to the minus 7. So if I work that out, I get 1 times 10 to the minus 14 divided by 4.3 times 10 to the minus 7, and that equals 2.3 times 10 to the minus 8. So if this was a question on a quiz or a test and asked you to verify this, we want you to show us that the Kb value is bigger than the Ka value. So although this amphiprotic compound would do both things, it primarily produces hydroxide ions. And if you look at just the powers, you got 10 to the minus 11, and you're comparing that with 10 to the minus 8. So really a 10 to the 3 difference. So basically a 1,000-fold difference here between the two of them. So it really is a basic compound, which is why the water turns blue. Now the ammonium nitrite, that would dissociate into ammonium, which we know is acidic, which might make sense why it's yellow in color, but it also produces nitrite. And so here we have another situation where we have more than one thing going on. So we know that this ammonium will produce hydronium, that rhymed, NH3 and hydronium. And we know that NO2 minus, now don't confuse this with NO3 minus, NO2 minus is actually a weak base. So it will take a hydrogen from the water, making HNO2, and it will also produce hydroxides. So here we have another situation, not that that's amphiprotic, but we have two different compounds that one being a weak acid, one being a weak base. And so we'd have to know which is overpowering the other one. So if we look at the Kb value so let's look at Ka first, that's easier to calculate. Ka value for ammonia, we did that previously. The ammonia NH3 is 5.6 times 10 to the minus, I just lost it, 5.6 times 10 to the minus 10. So a pretty small number here. And the Kb value would be equal to 1.00 times 10 to the minus 14 divided by the Ka of nitrous acid, which is 4.6 times 10 to the minus 4. And that gives me a value of 2.2 times 10 to the minus 11. So if I compare these two values, It's not as big of a difference here, but here the Ka value is bigger than the Kb value. So we would say that this is going to act as an acidic salt. So this salt here is an acidic salt, and the salt over here, that's actually going to be a basic salt. So this actually can be quite tricky if you have more than one compound that can do something. So amphiprotic compounds, you have to compare Ka and Kb, and that takes a bit of work to do that. So last question I wanted to show you, and this really bothered students last semester, and it was a smart class, had a lot of really smart kids in there, and we added aluminum chloride to the water, and the water turned red, like it was dark red, like it was really red. So if I look back on the slide, oopsie. And I'm thinking red. Well, in universal indicator, red here is pH less than 3, so it's really acidic. So you add aluminum chloride to water, and it gets really, really acidic, really fast. So if we look at the compound again, well, we know aluminum chloride is a salt. Once again, that's chapter 3, and we know salts dissociate into ions. That's not unusual for us to work with. But we know chloride ions, so chloride ions over here, we know they're neutral because they are the conjugates of the strong acid HCl. So they cannot act as a base. They cannot take a proton. Fluoride could, but not chloride. So this solution is acidic, and that means hydronium was made, which means something had to be an acid here. And I don't think anyone's going to think chloride is an acid. But what about aluminum? Aluminum ions. I mean, they don't seem like they'd be basic, because to be a base, you have to take a proton. You're already +3 with aluminum. I know taking another positive charge seems a bit unusual. But if it did, you would get the evil space computer from 2001, A Space Odyssey. HAL. I think he was the HAL 9000, though. This would be the HAL 4+. So that doesn't happen. That doesn't occur. But we know it's acidic. So what's going on here with this? Well, I want you to turn to your data table now. There's something really strange in your data table. You might have just looked over because it's so just awful looking. You probably just your mind just said, don't look at it. Don't look at that thing. It's so evil. And so what it is these compounds. Erase that. And let me see, underline this here. It's a fancy sort of word in the beginning here. Hexa. And these compounds are ions in water that form a sort of unusual complex that we're not going to get too bogged down with in detail. But notice that that's the iron 3 ion. This is the chromium 3 ion. This, however, is the aluminum ion. So this is what aluminum 3+ looks like in water. It actually, when you put it in water, you get this. It's actually an aluminum with 6 water molecules with a +3 charge. So when I go back to the other slide, what you actually get here is you get aluminum, and you have 1, 2, 3, 4, 5, 6. And so you get this weird structure that actually is the ion with a +3 charge. And so this molecule, or structure, I guess I should keep it that way, it actually can now act as an acid. And so when it comes in contact with water, what happens is one of the H's of one of the water molecules is moved over to that. So before we write the products here, let's sort of let's write this. This would be aluminum with 6 waters and a +3 charge. And now we're reacting it with H2O. Well, we know when we give a proton to water, we get hydronium, so I don't think that's going to surprise anybody. not going to knock your shorts off. But what about the aluminum with all these waters around it? Well, you would still have aluminum. Maybe I'll have to go down here. You still have aluminum. And now you would have 5 waters, but one of the waters would have lost an H. So now it's OH. Now, a lot of times students might get confused and, well, that's hydroxide. This must have a -1 charge.
Says that if a proton, so that's so as far as ions go, which is for the perspective of these things. So generally, certain ions, so sodium, potassium, calcium. So that's up to you for that's a final step. It's definitely a tough section. We can't go through all these. So questions, maybe. So driven down. Test later this week.
Stop the video. So hope you guys are doing well, and we'll talk to you soon.